Okay, so let's take a look at going from the Verilog to drawing a circuit, and we're going to do one of these of our own in a little bit. But this is, you're given the Verilog, and so these are the solutions that you already have online. And how would you come up with drawing this circuit? So the first thing goes that I said before, you see you've got an always block, you've got these Y's, you know you're going to have 3 flip-flops, so you draw the 3 flip-flops. You've got an if, so you have a pretty good idea that you're going to have a multiplexer. So you put the multiplexer on here. You've got a clock, so we're going to put the clock in here. Now, we also have this thing here that's called reset in. And so we know we're going to have that in there somewhere, so we'll put that in. And it can go to a flip-flop. But in this case, we're going to send it, let me look at this a little bit closer. Okay. Wow. All right. This reset in is just being used, it's just a variable name. So this would work exactly the same, and it always is just a variable name. So this would work just the same if I had print screen.
So it's just like a variable where you put on every single circuit you have?
It's just like our Y and the one we did a minute ago. So if I change the name of it to if not Fred, and I now have a variable named Fred, and Fred is the input into my multiplexers. This is saying if Fred is 0, so if not Fred, that means if Fred equals 0, then if Fred equals 0, then Y, and in this case, Y, we have Y0, Y1, and Y2, but we also can think of Y as just 3 bits of the 0th bit, the 1st bit, and the 2nd bit. And it says if Fred equals to 0, then Y becomes equal to 0, 1, 0. 0, 1, 0. So that means that the 0, 1, 0, this is Y2, this is Y1, this is Y0. So if the input to our multiplexer, whatever we call it, equals 0, then we want our Y to become 0, 1, 0. We want Y2 to become 0. We want Y1 to become 1. We want Y0 to become 0. And that happens when the input to our multiplexer is 0. So that's why it's going into the 0. Else, that means that Fred, or reset in, or whatever we call it, equals 1. Then Y0 is going to become equal to Y1 and X. So I've got a little AND gate, and I've got this variable X, and it's Y1 and X. And I have that Y1 becomes equal to Y0 or Y2, so I have the or of those. and I have that y2 becomes equal to x. All right. Okay, so let's do another one. Y'all pick one, because I'm gonna stay till 6, and then I don't know if I'll have, I will record the rest of them tonight, but y'all, which ones would y'all like me to do next?
Wait, we didn't do part B? Wait, part D, my bad. 5D.
I think I did. Oh, I didn't. You're right. I didn't. Okay, so let's do D. Okay, so we have a what size counter? 4-bit counter, and we want it to count in this sequence. So we can assume that our counter works. We don't have to like do anything special to make our counter work. It will have a load, and it will have its outputs Q0, Q1, Q2, Q3, and it'll have its inputs. Don't know what I've called those before. Do you know what we usually use? Is it D? D, okay, I'll use D. So D0, D1, D2, D3. A lot of times you have, well, you should have an enable. And for ours, enable, you're just going to have a 1 going into the enable because you want it to be enabled. There's no reason not to have it enabled. And so a 1 into the enable, and you'll have a clock, and the clock just goes into the clock. Okay, and then when it starts its sequence, it's loading the number 5. So we want to see what 5 looks like. 5 is 0, 1, 0, 1. This is D2, D1, D0, D3, D2, D1, D0. So I want to load D3 is 0, D2 is 1, D1 is 0, and D0 is 1, because that's the value of 5. So whenever it's time to load, I want it to load that. Once it loads 5, it will count on its own. That's its job. You don't have to make it do that. So once it loads 5, it'll count 5, 6, 7, 8, 9. You don't have to worry about that part. That's done. What you have to worry about is getting it to stop at 9. So to stop at 9, you need to figure out what the number 9 looks like. 9 looks like 1, 0, 0, 1. So whenever you have a 1, 0, 0, 1, you want it to stop, and you want it to load 5 again. So that means at that point, Q3 will be 1. This is Q3, Q2, Q1, Q0. This one is the same forwards and backwards, but if it's not, make sure that you have them labeled right, because we read them in the opposite direction a lot of times as we write them. And so we want it to stop. You're not actually going to write these values in the way I have them there, but that's what we're looking for. And so we're looking for when we have a 1, 0, 0, 1. So if we wanted to be super safe, we could do the AND of that being 1, the not of that, the not of that, and this being 1. I could do the AND of all of these. And I know when that's true, then it's time to load. Because when I have a 1, 0, 0, 1, that means I've got a 9 and it's time to load. Now, usually, oftentimes it'll work out if you just catch the 1s. You don't even have to catch the 0s. And that would work out here. You don't actually have to have the 0s in there because that would give you the value that you would need. Okay, so that was 5D. What's the next one you want me to do? And any of you, if you need to go, you can go ahead and go.
I like to do 6.
6. Is everybody okay with 6? Okay. Have y'all talked about Mealy and Moore yet? No. Okay. So you can skip anything where it says if it's a Mealy circuit or a Moore circuit. Okay. This is a good one.
Thank you.
You're welcome.
Everything's being recorded.
Looks like it. Thank you for checking.
Thank you so much.
You're welcome. For those of you who are leaving, do check the recordings because some of them are different from ones that we've done. So just take a quick glance.
And you
at
said
it.
you're going to be posting the rest of these?
Yeah, I'm gonna do it like as soon as I get done. That's why I brought 2 computers just to be able to upload as soon as I get done with it.
Okay,
Yep.
thank you.
So actually, let me go ahead and, well, I'll post that in a second. Okay. So give the state diagram for a circuit that detects the sequence 0, 1, 0 and gives an output of 1 on the next clock cycle after the sequence is detected. Otherwise, the output is 0, overlaps are allowed. So this is just like what y'all did for your lab today. So we want to think about our paths towards getting this sequence 0, 1, 0. So a 0 gets us 1 step of the way. A 0, 1 gets us the next step, and a 0, 1, 0 means we have it, and we can output a 1. And so you're always going to have your reset state, and we want to think about from our reset state what happens if our input is a 1 and what happens if our input is a 0. If our input is a 1, have we gotten anywhere towards our pattern? No.
Then you go back to reset.
Right. So I'll put in T, I'll call it T equals 1. What about if our input is 0?
You do get somewhere, you get 0, then you get 0.
Yeah, so now I'll call this state A, this state B, and this state C. So I'm going to state A. All right, now if I'm in state A, I have a 0. If I get a 0 from here, I would have a 0, 0. If I get a 1, I would have a 0, 1. So if I get a 0, where am I now?
You repeat it.
Yeah, I'm still back at A because I still have a 0. And if I get a 1,
you go to new state.
And I'll go to the state I called state B. Because state B is the state where I have 0, 1. Now I have a 0, 1. From 0, 1, I could get a 0, 1, 0 or a 0, 1, 1. So if I get a 0, I'm at 0, 1, 0. So where do I go from there?
If you get 0, 1, 0, you get a new state.
And that's state C. And that's if my input was 0. What if I get a 1?
It goes back to reset.
It goes all the way back to reset. And let's see, if I go to state C, then my output is 1, and for all the others, my output is 0. Now if I'm at state C, I have a 0, 1, 0. If I get a 0, I'm at 0, 1, 0, 0. Where do I go?
You go to A.
I go to A. And if I get a 1, I would have 0, 1, 0,
So
1.
you go to B.
0, 1, I would go to B. So that is my state diagram. My state table would look like this. Did I not call the reset anything? Okay, I'll call the reset Z. So my reset state is Z. So Z, A, B, C. Z, A, B, C. Yep. So if I was at Z and I got a 0, I went to A. If I got a 1, I went back to Z and my output was 1. If I was at A and I got a 0, I stayed at A. And if I got a 1, I went to B and my output was 0. Output should be 0 in all of those. If I was at B and I got a 1, I went back to Z. If I got a 0, I went to C, and my output was 0. And if I'm at C and I got a 0, I went to A. If I got a 1, I went to B, and my output was 1. Okay, now the next part of this is a little bit different. It says make a state assign table and use one-hot encoding. So if we didn't say to use one-hot encoding, how many flip-flops would we use?
We'd use 3. 4? Oh, no, 4. I'm sorry, I'm 4.
2, because we have 4 states. 2 to the 2 equals 4. So you need a minimum of 2 flip-flops. But one-hot encoding means we are going to use 4. So one-hot encoding means that we make in each state exactly 1 bit is hot. So this would be 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, and 1, 0, 0, 0.
You basically just square what would have been the original, because like we were supposed to have 2, but since we're doing a hot encoding.
No, you have 1 for as many states as you have. Every state has its own. So there are 4. If I had 5, I'd have 5. If I had 6, I'd have 6. It's just, you see how I'm putting the ones?
Yep. And it's kind of.
And so all I did there was just replace A with, well, Z with 0, 0, 0, 1, and A with 0, 0, 1, 0, and B with 0, 1, 0, 0.
Well, isn't it? Well, it's supposed to be 3 bits, but since we're doing one hot encoding, we're doing 4 bits.
It would only have to be 2 bits because 2 to the 2 is 4. If I was using the minimum number of flip-flops, then I could do 0, 0, 0, 1, 1, 0, 1, 1. One hot encoding means that you only have one 1 in your entire number.
1 1 for your entire number.
In this whole number, how many 1s are there?
1 1. Oh, just okay.
But in general, however many states you have, if I had 20 states, how many flip-flops do I need?
I would say
Well, 2 to the third is 8, so what's 2 to the fourth?
16.
So what's 2 to the fifth?
32.
So I need 5 flip-flops.
Oh, so you always pick the one with the hot in it.
I need, this shows me the maximum number of states I can have.
Okay. Oh.
All right, let's do,
Wait, you answered that was H?
that was H. And I might skip 7 since y'all said y'all haven't done mealy and more yet, because that's the main point of 7. We did 5. Let's do 4.
Question about
Yes.
this.
Yes.
So this is a different thing, but so if it's 1 1 and it's going to 0, like if its output's a 0, would it go back to 1 0 or 0?
Well, what are we trying to detect? Is this the one I just did?
Different one. It was for the
Yeah, so if you had,
So this is
don't let me forget to.
Because 110 is not an output we're looking for, but 10
Yeah.
it will still go back.
Yeah, I'll explain why. So I'm gonna do, instead of doing this one, or actually, do I want to do this one? No, I'm going to make it a little different from this. Okay, so I'm going to say let's make a sequence detector that detects the sequence 1 0 1 1. Yeah, we do 1 0 1 1. So we want to think about the ways to get to 1 0 1 1. So it can be, so what this means, 1 0 1 1, is that the last 4 bits entered were 1 0 1 1. So the last 4 bits entered were 1 0 1 1. So the one step on the way is if the last bit was 1, and then if the last 2 were 1 0, and the last 3 were 1 0 1, and finally the last 4 were 1 0 1 1. So when I start with my reset, if I have just a 0 and nothing else, that doesn't fall into any of these categories. So that's going to bring me back here. If I have a 1, that brings me to this one, where my last bit was 1. Now from this 1, if I get a 0, I'll go to here where my last 2 bits were 1 0. But if I get a 1, I'll come back here where my last bit was 1. And so this means that what it looks like is 1 1, but I still have my last bit as 1. And then from 1, 0, if I get a 1, then I'm going to this next state. And if I get a 0, my last bit is none of these. None of these. So I'll go back here. Okay, so you see how you do it? Yeah. Okay, and since I'm recording this, let me go ahead and finish. And then so this was 1. And then from here, if I get a 0, then I have 1, 0, 1, 0. And that would bring me to this one. So that would bring me to this one. If I get a 0, and if I get a 1, that'll bring me to this one. And now, let's see what happens with this one, with 1, 0, 1, 1. If I get a 1, my last 2 bits are 1, 1. That'll bring me to this one, where my last bit is 1. And if I get a 0, 1, 0, 1, 1, 0, 1, 0, that'll bring me to this one. Yep, okay. And
Yep, let's do number 4.
okay, number 4 it is.
Thank you.
You're welcome.
Oh, wow, really?
Yep.
Okay, I'm privileged.
Okay, so here we have our register described to us, and so it's described, and we're going to draw it and do the Verilog. Well, it tells us.
Yeah, I totally read
And it tells us that if I read ahead, I haven't read all the way ahead, but I see it's got an if in here, so I feel like I'm probably going to have multiplexers.
How many bits of multiplexers? How many it can be like?
It tells us. So it told us that it was a 4-bit register
Oh.
right here. That's how we know. I don't know what this thing is in front. I'm going to draw on Word. Nope, this is a PDF, so I'll draw on the PDF. Okay, so it has serial input left in. So that means I have a variable left in that goes into the leftmost flip-flop. And serial output right out. So it looks like I'm probably not going to need this last multiplexer right here. Nope, I am going to need it. I am going to need it.
Why did you know the left one would be totally in the left and the right?
What did you just say? Say it again.
Oh yeah, I know, it says left in and right out. True, but like, does it,
That's what it means.
okay?
Yep.
I thought it was just like a variable. Name.
Well, it is, but that's why it's called that. It does depend a little bit on the person who wrote this question is a person who would always number the flip-flops like this. And so when we talk about shifting right and shifting left, we mean shifting right, we mean shifting to least significant, so going from bigger number to smaller number, and shifting left means going from smaller number to bigger number. So if you had numbered these the other way, you shouldn't have, probably, but if you had, then that means you made left right.
Okay.
So we are going to need this. Okay, so it has parallel input W03, so that means we have W0, W1, W2, W3, and parallel output Y03. Okay, if the variable named signal is 1, so I have signal, and that's going to be my variable, and that's the if, so that's what's going into the multiplexers. And if it is 1, oh, I remember writing this, and this was a bad problem. Yeah. Yeah, so this should be, this is contradictory. Okay, so if the variable name signal is 1, the register should shift values right using the serial input left in as the input for register 3. So that also tells you. And serial output right as the output for register 0.
Yeah.
So if we're going to shift rights, that means if it is 1, so that means my left in should really be going into the 1 of this first multiplexer. So each one of these is going to go into the 1 of the multiplexer coming after it. If the variable name signal is 0, it should load W. So it just means W is going to be loaded.
I just put W, or do you have to do W brackets of this to which one it is?
No, you need to do brackets as to which one it is.
Oh, it's like each W could be a different one.
And then the output is just going to be the output from each one of these. And this doesn't really have anything to do with whether signal is 0 or 1. It's always going to output, so it's just kind of an extra thing. You don't have any choice on it.
Wait, is this supposed to be W3 all the way to W0?
Yes, I did it backwards. Thank you.
No, of course.
And I caught myself on the bottom one.
Okay, the pattern it says the output. Well, where does it say the output is also equal to the next upcoming multiplexer? That's what I was confused on.
Well, the output is always going to be the output from each multiplexer. That's just that's understood.
Oh, so like if I'm gonna do multiplexers,
I did it right.
you would say a definite key would always be like going to the multiplexer.
So anytime I'm going to say, if I say the output is whatever, it'd be the out. If I don't say the output from a particular one, it'd be like that.
Also, like if not stated what the input of the multiplexer, you just assume it's the output of the. Okay, that's interesting. I think this is gonna be the hardest problem.
Well, this I wish I had remembered that this is I wrote this problem and it's a bad problem, and I wish I had remembered that. So I'd rather do, if I'm going to do the Verilog, do one for one that's not poorly written. So let me see.
Yes.
Let's just instead
Have another problem on that?
I'm going to do one. It's similar, so it's not exactly the same. I want to take care of something first before. Okay, so this is a different problem. Let's say that we have that we need to write the Verilog that goes with this register right here. And let's see what the description of that one was. It says the register below. Actually, let's just go ahead and do this problem the way it is, but then we're going to also write the Verilog for it. The register below can hold its value or shift right with serial input, serial in, and serial output, serial out. Draw a similar register that can hold its value or load a new value in parallel. So, so this one, we see that it can hold its value because if you look at the output is going to the input of the multiplexer. And so it holds its value when this variable yellow is equal to 0. And when it's equal to 1, it has serial 1 and it is shifting right here. So we're supposed to draw one that can hold its value or load a new value in parallel. So we would have it doesn't say for what value of the variable it does what, but let's say that it holds its value when this variable named yellow equals 0, and when yellow equals 1, it loads parallel the variable w. So 0, 1, 0, 1, 0, 1. So here's our variable. And when it is 1, it holds the same value. The output of the multiplexer goes into the flip-flop. And when, oh, I put it into the 1, so that's holds value when yellow equals 1. When yellow equals 0, it loads W into parallel. So I'm going to call this flip-flop 2, flip-flop 1, flip-flop 0. So this would be W2, W1, and W0. Okay, so how would I write this in Verilog? So I will have module register question, and I'm going to have my input, what did I call it, yellow. I'm going to have an input W. Did I have anything else? Did I have clock? Except I don't think, well, yeah, we'll have a clock. Well, no, we don't need the clock on this one. Well, if I need anything else, I'll come back and put it in. So I'll have input yellow, input 2 colon, is it 2? How many bits was it? It's 3 bits. 0, 1, 2. 2 colon 0 W. And then I'm going to want to have I'm going to be changing my value inside an always block, so I'll have it be a reg. So I'll have reg20, and I will call that Q. And I'll have always at yellow W. No, I don't want it just when, I'm only going to want it to change when yellow changes. So I'll just have always at yellow. If yellow, that means if yellow equals 1. If yellow equals 1, okay, so I'll need an integer here because I'm going to have a for loop. If yellow, then I'll have begin 4. And let me do this correctly for Verilog. Open parentheses. J equals 0, semicolon, J less than 3, semicolon, J equals J plus 1, semicolon, not semicolon. Actually, I'm going to want to have my if inside here. So I'll go through, and here's where I'll check what I'm going to do. It'll be inside here. So if yellow Q of J becomes equal to Q of J. Not really necessary, but it just kind of helps you like keep track of what's going on. Else Q J becomes equal to W of J. And you could do this without a for loop, since we're doing the same thing to every one. You could just have always at yellow, and you could just have if not yellow, Q becomes equal to W, and that would do it. And we actually don't need to begin here, because the only thing inside our always is a 4. And everything just has one line, so we don't need anything other than an end module. And that ought to do it. All right, well, I have to go. So good luck, and I hope y'all do great.